So in this video I want to have a look at centripetal acceleration and force, and in particular I want to have a look at these two equations here. The one on the left here is for centripetal acceleration, which is omega squared times r, or v squared over r. The one on the right here is centripetal force, which is m, the mass, times omega squared times r, or mass times v squared over r. Now if we take this circle here as representing the motion of a particle, let's say the particle starts here and it moves in an anti-clockwise direction. It's going to move in this direction here, and let's say it's up at here at some stage. It makes an angle of omega here with the radius r. Omega is going to be defined as the angular speed. Its units are going to be radians per second. And let's say v then is the speed, and it's going to be, this can be defined if you like as the linear speed. The units are going to be in meters per second. So if we take the particle as traveling from here to here in 1 second, then this distance, this part of our circle, is going to be a distance v, if you like. So we know also that this sector of a circle here has length equal to r times theta. The length that we want is this distance here. So L here is v, the distance that the particle has traveled in 1 second, r is r, and the angle then is just omega. That's the angular distance that the particle has traveled in 1 second. So this is our formula here, and this can also be written as omega equal to v over r. So this formula here is going to link the linear and the angular speed of a particle traveling in circular motion. So what I want to prove in this second section here is one, that acceleration is going to be directed towards the center of the circle, and two, I want to prove that the magnitude of the acceleration of a particle moving in circular motion is going to be omega squared r, or we can write it as v squared over r. So let's start then. We're going to start with a circle. Let's say the circle has a radius out to here, and let's say the particle has moved up to this position here. So it will have a position vector s, and let's say that distance out to there is going to be r. I'll just drop a line down here. The angular speed of the particle is omega radians per second. It does omega radians every second. So that means this angle here is going to be omega times t for t seconds. So let's see, this distance along here, in our right angle triangle is going to be r cos omega t, and then up along here this is going to be r sine omega t, if this is r up along here. We know that the particle is going to be here, so its position relative to this point here, let's call it O, is going to be s, let's say, and its position vector is going to be r cos omega t in the I direction plus r sine omega t j direction. So this is our position vector of our particle after it has travelled in an anti-clockwise direction at an angle of omega times t, and this is our position vector here. So we know that if we differentiate this, it should give us our velocity, the velocity of our particle. So let's do that. So what we want is to find the velocity vector. That's going to be equal to d of our position vector, or displacement vector, with respect to time. So if we differentiate this first here, we're going to get, well, if we differentiate cos, we'll get minus sine. So it's going to be minus r times sine omega times t, but we've got to differentiate the omega t as well. So that'll give us omega, so I'm just going to stick that in there. And then we'll have sine omega t here. So this is the first term differentiated, and that's I. Let's differentiate the second term. Well, if we differentiate sine, we'll get cos, And the same thing will happen here. We'll end up with or omega cos omega t in the j direction. So this is our velocity vector here. So let's go one more step now and do the acceleration vector. So acceleration then is just going to be velocity differentiated. So it's going to be d velocity differentiated with respect to time. So again here we've got to differentiate this and we've got to differentiate this here. So if we differentiate sine, we'll get cos. So it's going to be minus or omega cos omega t in the I direction. However, we've got to differentiate this as well, which will give us omega. So that's going to be squared here. Let's do the same here. If we differentiate cos, we're going to get minus sine. So it's going to be minus or, again, omega squared sine omega t in the j direction. So what I'm going to do here is just factorize out minus omega squared. That'll leave me with or cos omega t I minus, sorry, it's going to be plus actually, because I've already factorized out the minus. So it's going to be plus or sine omega t the j direction. Now let me just move this up a little bit here. We can see here that inside the bracket here is just a displacement vector. If we go back up here, we can see the displacement vector here is or cos omega t I plus or sine omega t j, and that's what we have inside our bracket. So let's just replace that then. So we've got minus omega squared times our s, our displacement vector. So what we've ended up with here is our acceleration is going to be equal to minus omega squared times s. So this shows us that the acceleration here, because of this minus here, we can see that the acceleration is going to be directed towards the center of the circle. So we can see that our displacement vector is in this direction. So our acceleration vector is actually in the opposite direction. So it's going to be directed towards the center of the circle. So that was the first thing we needed to look at. We needed to prove, if you like. So let's have a look at the magnitude of this particular vector now. So let's see, we want to find the magnitude of our acceleration vector. So that's going to be the square root of a squared plus b squared, if you like. So it's going to be, we're going to look at this particular version of the vector here. I'm going to look at this. So this is our a here and this is b here. So we're going to put those into our formula. So it's a squared. So that's going to be minus or omega squared cos omega t squared plus minus or omega squared sine omega t. Okay, so let's see what happens if we do all of this out here. Now, what I'm going to do here is square all of this. So you've got or squared omega to the power of 4 cos squared omega t plus, again, we've got or squared omega to the power of 4 sine squared omega t. Next thing I'm going to do is just split this square root up. I'm going to factorize out the or squared omega to the power of 4 and then split up the square root. So I'm going to put the or squared omega to the power of 4 here, and what I'm left with is cos squared omega t plus sine squared omega t. Now if we square root this part here, we'll get or omega squared, and we know from our trigonometry identities that cos squared plus sine squared is just going to give us 1. So this thing here is just going to be 1, so we end up with the square root of 1, which is 1. So we'll just simply end up with or omega squared. So this is our acceleration, centripetal acceleration, and also because we know from part 1 of this video that omega is equal, we know that omega is equal to v over r, we can just substitute that in here. So we get or v over r squared, which is or v squared over r squared, and that'll just give us v squared over r. So these are our two equations for centripetal acceleration, which is the second part of what we want to actually prove. So we have acceleration here is equal to r times omega squared, and we also have acceleration equal to v squared over r. So let's just move that on a little bit further. Let's just do a couple more things. So let's have a look at our velocity vector again. So our velocity vector was minus omega r sine omega t in the I direction plus omega r cos omega t in the j direction. So if we were to look at the magnitude of velocity in this case, so let's look at the magnitude now. What we've got to do again is the square root of a squared plus b squared. So that's the square root of minus omega r sine omega t, which we need to square, plus omega r cos omega t, which we need to square. Let's do this then. So let's see, we end up with omega squared r squared sine squared omega t plus omega squared r squared cos squared omega t. Now again, I'm just going to factorize out the omega squared r squared and split up our square root again. So we end up with omega squared r squared here, and again we end up with sine squared omega t plus cos squared omega t. If we square root this, we get omega times r. And this here again is sine squared plus cos squared is just going to be 1, so we end up with a 1 here. So finally we end up with omega times r. And this is our formula for the magnitude of the velocity. Let's just do one other thing, and that is just to show that the velocity vector and the displacement vector are actually perpendicular. So to do that, I'm just going to do dot product of the two vectors. So let's look at the velocity vector and the displacement vector. Dot product. So that's minus omega r sine omega t I plus omega r cos omega t j. We want to do the dot product with the displacement vector, which was r cos omega t in the I direction plus r sine omega t in the j direction. So to do the dot product, we just simply multiply these two and these two here. So let's do that. So minus times plus is going to be minus. We've got omega r times r, which is r squared. We've got sine omega t times cos omega t. So we leave out the i's when we're doing this, and we multiply these two here then as well. So again, we've got omega r times r squared. We've got cos omega t times sine omega t. If we look at this, we have minus omega r squared sine cos, and we have plus omega r squared sine cos, or cos sine here. So we do in fact get 0. Therefore we can say that the velocity vector is perpendicular to the displacement vector. Actually, I'll just do one more thing. I just talked about at the beginning, I spoke about the centripetal force. So let's have a look at that. So we know that force is equal to mass times acceleration. So in our case, we know that, well, we have mass here. Our acceleration is omega squared r. Or we can just say mv squared over r. This is our centripetal force. Okay, and that's really it for this video.